In this video, we're going to be talking about a very different kind of solution known as an alloy, which is where the solvent in your solution is a metal. So alloys are composed primarily of metals, but they are homogeneous mixtures. So they are considered solutions, even though they're very different from the things that we've been talking about. So an alloy is mostly metal. The solutes can also be metals, or they can be non-metals as well. So the reason why alloys are useful is that we use metal for a lot of things in society today. But the periodic table gives us a very limited list of options for metals to choose from. So if we're stuck with only pure elements as our choices for metals, we have a limited list, and each element has whatever properties it has. And if pure elements are our only choice, we better make use of one of those, or we're not going to be able to, use a metal for what we want to do. But what alloys allow us to do is essentially tailor the properties to the desired application. So if we're looking for an appropriate material for some application, and we need it to have a certain strength and a certain density and a certain melting point to make sure that it's safe and effective at whatever job we need it to do, there may or may not be a pure element that exists that checks all those boxes, but we can try to create an alloy that does. So alloys essentially give us an infinite number of options for types of metals when you think about not only the different elements that you can combine, but combining them in different proportions as well. So we're going to talk today about a couple different types of alloy structures that you can have, two different kinds specifically that are some of the most common types of alloys, as well as some of the easiest to identify. So in a pure metal, in a pure element, metals typically exist in some type of lattice structure, meaning that there are rows and columns of atoms, and alloys are more or less the same. But exactly how that lattice is going to form and exactly what it's going to look like depends upon the elements that are being combined. So different elements combine into different types of structures or different types of alloys. And we're going to talk about two today. So the first type that we're going to talk about is known as a substitutional alloy. And in a substitutional alloy, atoms of the solute essentially just directly replace atoms in the solvent lattice without really disrupting things very much. And substitutional alloys occur when your two atoms, your two elements that you're combining, are very, very similar in size and similar in radius. And things are going to be similar in radius when they're relatively close together on the periodic table. They don't have to be right next to each other or anything. But the closer they are to one another, the more similar they're going to be in radius. And the less disruption there will be when solute particles replace solvent particles. So one of the most common substitutional alloys that you will encounter in the world is brass, which is a combination of copper and zinc. There are multiple types of brass, but most of them are mostly copper. So copper would be considered the solvent, and zinc would be the solute. But proportions can vary widely with things that we call brass, depending upon the application. The most common type of brass used in musical instruments is known as yellow brass, which is approximately 2/3 copper to 1/3 zinc. Other types of brass can be used for musical instruments as well, and the type of brass actually affects the sound of the instrument somewhat. The tone of it will vary slightly because of differences in the way the atoms vibrate, and therefore the difference in the sound that they create. So if we look at a representation of pure copper and pure zinc, in each of these two pure substances, we have the atoms arranged in a lattice structure, meaning that they're in rows and columns in 3 dimensions, a nice organized structure for these atoms. When these two things combine, if you find copper and zinc on the periodic table, you'll find that they're right next to each other. It means that they're almost identical in radius. So they're definitely going to create a substitutional alloy, which means that we will end up with a very similar looking lattice structure, but with zinc atoms dispersed throughout. So the zinc will just be randomly distributed throughout the copper, the primarily copper matrix that's still in place here. And that is our alloy. So the other type of alloy that we can create, or that we're going to talk about anyways, there are other ones, but we're just focusing on these two, is known as an interstitial alloy. And in an interstitial alloy, solute atoms actually fill up the empty spaces in between solvent atoms. So this one is a little bit different, that the solute atoms are inserting themselves into those empty spaces. If you think about rows and columns of spheres, atoms are essentially spheres, there's going to be empty space in between. You can't entirely fill up every little bit of space in there. And it's those empty spaces, which are known as interstices, which is where the name comes from, that the solute atoms are just kind of going to weasel their way in there. Fill those up in our interstitial alloy. And in order for that to happen, those solute atoms have to be really small. They have to be much smaller than the solvent atoms. So this happens when the solute atoms are much smaller than the solvent atoms. So usually for interstitial alloys, this is often when you will see nonmetals as the solute, things in the upper right corner of the periodic table are going to be where you find really, really small atoms. So those tend to be good solutes for this type of alloy. And that is the case in the most common interstitial alloy that you're likely to encounter, which is steel. So steel is an alloy composed primarily of iron with a little bit of carbon mixed in. So most steels are about 2% carbon by mass or so. It can be more or less depending upon the exact application. So mostly carbon, sorry. said that wrong, mostly iron with a tiny bit of carbon mixed in. And those carbon atoms are filling in the holes. So if we think about the two pure substances first, again, we have a lattice type structure, but this time all that's really going to happen is these little empty spaces in between our atoms in the iron lattice, some of those are going to get filled up by carbon atoms. So here we can see that in these interstices, in these little holes in between the iron atoms, there are some carbon atoms inserted in there. So this picture really has too much carbon proportionally, probably. It's just a little bit. But with interstitial alloys, what's kind of interesting is that the total volume doesn't really get a lot bigger. You're just filling in some empty space in the original iron lattice. So interstitial alloys tend to be heavy and dense and often quite strong, as long as you get your proportions right. If you fill up too many of the interstices, they can get brittle. But that's where the strength and heaviness of steel comes from, is that you're really just taking iron, which is already pretty strong in and of itself, and filling in some of the empty space and making it even denser. So we can also have alloys that do both at once, where you can have multiple solutes dissolved in your solvent and end up with an alloy that is both substitutional and interstitial at the same time. So an example of this is stainless steel. So alloys can be both at once if you have multiple solutes. Having multiple solutes doesn't necessarily mean that you are both types. If you have multiple solutes and they're all pretty much the same radius, it's just going to be a substitutional mix of all of them. Same if both of your solutes are really tiny. But in the case of stainless steel is mostly iron with some chromium and some carbon. So it's steel plus chromium. And chromium is particularly notable for its resistance to oxidation. Rust is oxidation, is the chemical process that's happening when something rusts. And the addition of chromium into this prevents that, because chromium is really hard to undergo that process. So adding chromium to steel gives you something that is really, really strong, as well as really, really rust resistant, because you're getting that property from the addition of chromium. So it's still mostly iron by mass. Usually somewhere in the ballpark of 10% chromium is added, along with the same 2%-ish of carbon, and the rest being iron. So in this case, when we look at the pure elements by themselves, if we find them all on the periodic table, you will find that iron and chromium are quite close to one another, that they're 2 spaces away in the same row of the periodic table, meaning they have very, very similar radii. So those two will undergo a substitutional-like arrangement. But then compared to those, carbon is way up near the top right-hand corner of the periodic table. Those atoms are much, much smaller. So those are going to insert themselves into the spaces between the atoms. So that's how we end up with this arrangement that's sort of both substitutional and interstitial at the same time. One of our solutes is very similar in size to our solvent, and the other one is much, much smaller.